Yeah.
Good afternoon, everybody. Welcome to the class. So in today's class, I'll be presenting my work. This is my dissertation work on causal neurosymbolic AI, a synergy between neurosymbolic and causal AI and its industrial use cases. So a little bit about myself. I'm a PhD candidate here at the AI Institute under Dr. Amit Sheth. So you might have seen us roaming around here and there during your classes. So I have a quick question to ask you guys. Very important, pay attention. If I give you two choices, chocolate and a peanut butter, which one would you choose? How many for chocolate? 1, 2, 3, 4. Okay, 5. What about peanut butter? Yeah, peanut butter. Both, right?
Race cups.
Yeah, so tough choice to choose between a chocolate and a peanut butter. But what if I give you the best of both worlds? Chocolate peanut butter cup. That's what causal neurosymbolic AI is for me. It's the best of both worlds. It's the best of causal and the neurosymbolic AI together. So I'm going to talk about in detail about this slide in the future, like after a couple of slides, but that's what I'll tell you how these two merge together and makes the best of both worlds. So my talk has two major outlines. So in the first part of my talk, I'll talk about or I'll explain you what is causal AI, some of the primary concepts about it. In the second half, we will talk about the causal neurosymbolic AI part of it. What are the use cases? How do we represent it? What are the type of use questions that we can help, that causal neurosymbolic AI can help us answer? So just stepping back, what is causality? As humans, we think causally. In day-to-day life, in our everyday tasks, whatever we are thinking has a causal notion behind it. So the fact that you came 5 minutes early, that caused you to settle down, open your laptop, get ready for the class. These are all causal thinkings that as humans we do. So causality is nothing but a relation between two entities where you have this concept of A causes B. It is at the core of everything we see, we do, or we imagine in this world. And you might have heard about this, that correlation is not causation. This concept about spurious correlation, and sometimes people tend to think that correlation is causation. So for example, if we have a high correlation between young drivers have a high probability of being in an accident, that does not mean that the young drivers are actually causing the accident. We just have few instances in the data which shows that the young drivers are more likely to get into an accident. And here's a image I have. So the person is saying everybody who went to the moon has eaten chicken. So does that mean chicken makes you go to the moon? So there's a high correlation between eating chicken and going to the moon. That's not true. Many of us here are non-vegetarian, eats chicken. Does that mean we get to go to moon? Probably not. So the correlation between chicken and going to the moon does not mean that's actually will cause us to go or travel to the moon. So why does that happen? Why does people tend to say correlation is not causation, or correlation could be a causal relation? Or why do we even make these type of assumptions or these statements? The reason being that when people are analyzing the data, they are just bombarded with the huge amount of data they have. They have hundreds of millions of variables. And just to make sense out of it, we randomly just do data analysis without even thinking about what is the hypothesis that we are trying to solve. So there might be some unobserved variables. So in the case of going to the moon, does it has to do with the education level? Could have to do with the nationality of the person, could have to do with the training or where the person is, which led to them to go to the moon. So this particular thing is known as data degradation, where instead of starting with an hypothesis and testing it, we just randomly take our data and just run multiple analysis or multiple methods just to make sense out of it. There's another concept in causality, which we call as counterfactual, which also we use it in our day-to-day life, which is basically what-if scenarios, where we are imagining or hypothesizing, what if something else would have happened? So what if I was 5 minutes late to the class, what would have happened? Would the door be closed, or would the class would have been canceled, or was it I'm not allowed to get into the class? Would I have missed 50% of the lecture? So all of those questions are hypothetical or counterfactual questions or imaginary questions. And this is very beautifully being portrayed by Robert Frost in this poem, The Path Not Taken, which if some of you might have read it, it's a poem where there's a passenger or there's a traveler who's taking a path in the forest, and he's encountered with two separate paths, left and right, and he's confused which one to take. And the entire journey, he's thinking, what if I had taken the other path? How would my journey would have been? Would my journey would be more peaceful, more beautiful views? So all of those questions that the traveler was asking are those hypothetical or counterfactual questions. So what would be counterfactuals in AI? We are all computer scientists. So let's say we have this scenario here where the human is sleeping and the robot comes and starts vacuuming. And the human yells at the robot and says, "You should not have woken me up." So that's a counterfactual. What then the robot, what did should robot understand? That I should not vacuum at all? No, right? The robot should understand that I should not vacuum when the human or anybody is sleeping in the room. So understanding these cause and effects, the sound of the vacuum actually caused the human to get up. So understanding these cause and effect relationship is extremely important in the AI systems. So some of you might have or might not have seen this image. So this is a ladder of causation by Dr. Udapul. He's the main, he was awarded Turing Award in, I believe, 2022 for his work in causation. And he came up with this ladder. So he had 3 rungs of this ladder of causation. So the bottommost rung is the seeing, where he says, where you're just observing the things around the world or around you. And some of the questions from these observations you can ask is, what if I see this, or how would seeing X would change my belief in Y? So he gave an example in the medical domain. So what does a symptom tell me about a disease? So you are just observing, you are not doing anything else. You're given the data and you're asking these questions. So that's what our current AI approaches does. They just are based, these are known as associations. So they're using associations based on the observational data. And that's what current correlation-based machine learning also does. Then the second ladder of causation is doing, where you're actually going and intervening or changing something in your AI systems or in your data set. So you're intervening, you are asking, what if I have done something differently? So some of the questions that in the case of medical domain is asked, what if I take aspirin? Will that cure my headache? Then the topmost ladder of causation is imagining. That is the counterfactual. You are hypothesizing, you're imagining, was it something else that had happened? Is that the reason my model performed in a certain way? Was it that I had set the hyperparameters to 10? Was it is that why my accuracy was 100%? So in the case of aspirin or headache, it could be, was it the aspirin that cured my headache, or was it that I took a short nap that cured my headache? So those are the counterfactuals that we can ask. So we need to basically create artificial general intelligence systems. We need to go from these observational level data set or data on approaches to the future hybrid approaches, which can understand cause and effect relationship in the data and in the system. So the main thing about causality is we start with a causal network. So a causal network is a Bayesian network where the relationship between each node is a causal relationship. So what the Bayesian network on the top is telling me that C is causing A is causing B is eventually causing D. And these nodes have certain roles in this relationship. So if you see on the right-hand side, in that particular relation where A is causing B, the first node is a treatment node and this lastmost node is the outcome node. So A happened and then B was the outcome of it. If you look at the second figure there, where A causes B causes D, A is the first node, so A is the treatment node. B is a mediator because that is an intermediary step between the treatment and the outcome, and D, which is the final node, which is hence obviously the outcome. And we have some examples here in the table, so we can look at the lastmost row, where if you look at the relation from C to A to B to D, what would be the treatment here? So in this case, the treatment, that is the first variable or the first node, which is the C. So C is the treatment. The final node, which is the D. So D is the outcome. And the intermediary nodes, B and A, they are the mediator relations. And I'll show you how we're going to use these concepts in the causal neurosymbolic framework later on. So I talked about causality. Now look at the other half of our problem or approach or methods, which is neurosymbolic AI. So what typically happens is in industrial use cases, we have lots of data that industries have to analyze and valuable data. So how do we make use of those data sets? And typically you would have an industry partner or researchers which have their own expertise and they'll tell you this is how you need to look at the data, or this is how you need to analyze the data. So making use of these assets, which is the domain knowledge and the data on the concepts, to derive some actionable insights for solving a decision problem or some issues that the industrial use cases can have. So neurosymbolic AI is further divided into two separate parts. The symbolic AI, which consists of the knowledge graph, rules, ontologies, logics. They have reasoners, which you can run on the ontologies and get explanations. So symbolic AI is known to be interpretable. Once you have decided a rule, so the rule for example, the class is don't be 5 minutes late. So that's a rule that's easily interpretable. Everybody can understand it. After 2:25, you'll be late. Interpretable, verifiable. You can verify it using a clock. Yes, it is 2:25, I am late. You can have done reasoning on it. It is data efficient and the expert knowledge is easily incorporated within those rules. So the expert knowledge, for example, in this case would be the fact that you can read your watch, the fact that you can understand that 2:25 is actually late. The second half of it is a neural network. So we all know neural networks are scalable. Most of you might be using neural network techniques in your projects this week. They are flexible, they are easy to use, but they are very good in handling noises, but they are black boxes. So when you combine these two together, symbolic AI provides you interpretable results, explanation. Neural networks are scalable, and they both can be used to make these black boxes more explanation or user-friendly. So this also comes as described as the best of the both worlds. So they increase the performance, they are generalizable, they are trustworthy because you can explain the results that you get, and they're easily scalable. Now coming to the two merger, our peanut butter chocolate cup, the Reese peanut butter chocolate cup. So causal neurosymbolic AI is again a fusion of the causal AI and the neurosymbolic AI, and it combines the strength of causality, neural networks, and the symbolic representation in learning. So I have these two arrows on top of in this diagram here, and my research deals with the top half of the arrow. So these arrows are telling us, so the top arrow, the red arrow, basically says you use the representation of causality from causal AI, you enrich or incorporate the representation of causality from the causal AI into the symbolic space, which is the logic, ontology, neural knowledge graph space. And then you use neural symbolic AI techniques to solve a particular task. The bottom arrow says you use the causal representation or the representation of causality from the symbolic AI part, which is the logic, knowledge graph, ontology, and you use the causal AI techniques to solve a certain task. So hence you can see on the red arrow, you take the representation from causal, the techniques are from the neurosymbolic AI, and the bottom arrow, the symbolic AI has the representation and the techniques are from the causal AI. Why do we want to do that? So Causal AI can help us understand the cause and effect in the data. Symbolic AI uses the logic-based methods, which are good for planning, problem solving, or reasoning. Neural networks use their capabilities to learn from large amount of data or to learn patterns. Causal AI uses the models like Bayesian network, structural equation model to represent these relationships. Symbolic AI structure the information in a way that is easily understandable by machines, and neural networks can obviously automatically discover the representation needed for classification or the feature extraction kind of a problem. What could be some of the benefits? So we already know some of these things are more explainable than others. So one of the benefit is that when we combine the causal models, symbolic reasoning with the neural network, it makes our decision-making process more transparent. So now you know that there's a relation exists between A causes B, it's already embedded in the logic. And if your neural network is giving a result, you can easily go back, trace, and explain why there is a higher probability or higher feature between A and B. It provides understandable explanation for predictions made by neural network. It is extremely critical for industrial use cases where safety, compliance, and accountability are extremely important. They are robust and generalizable. So you can leverage the causal inference to improve the robustness of AI models. So if you change any data distribution, these models would still run and would still be able to give the result what they're supposed to. They can enhance generalization by incorporating prior knowledge. So prior knowledge is embedded into knowledge graphs and causal relationships. We can do interventions. So that's what we learn in the second rung of ladder of causation, which can allow us, we can develop an AI system that can predict the impact of interventions and make informed decisions. And integrating the causal reasoning with neural networks can enable us adaptation to a new environment. So we talked about what are the benefits, very nice, but obviously everything comes with a challenge. So what are some of those challenges in this field? Since we are combining all three of these techniques together or three of these different fields together, there's a challenge of it. The huge problem that comes is how do you deal with complexity? So how do you combine all of these symbolic, neuro-symbolic, or neural network and causality, which is the Bayesian network approach? So combining these different types of models and reasoning system, data requirement, everything has a different data requirement. You cannot run neural network on a small amount of data. Typically, they give you good results. They need to stabilize. For that, they need large amount of data. So effectively, causal inference also requires rich, high quality data, which may also not be available most of the time. Scalable, since you're combining everything together, how do you make sure they are able to scale well to handle large data set and complex tasks? So combining the strength of these relations, we aim to basically create a systems that are powerful, efficient, interpretable, and they are capable of reasoning about cause and effect. What are some of the industrial applications that we can leverage these causal AI techniques or where causal AI can help? So causal AI is extremely good when it comes to unobserved data. So if you remember the topmost ladder of causation, which was counterfactual, where we were just imagining things. What if I had not taken, or was it the aspirin that cured the headache, or was it the nap that I had taken? So they're extremely good in analyzing things which are not observed. So it might not be in the data, but we can still run those counterfactuals or have those counterfactuals relations. So due to that capability, causal AI is extremely good for explaining unobserved rare events using counterfactual types of questions. In the case of a factory, we want to do, or a smart manufacturing setup, the issue or the use case that we want to do is root cause analysis. If there's an anomaly in the assembly pipeline, we would want to answer or analyze what is the cause of an anomaly, where did it occur, why did it occur, and how can I mitigate it? In the case of autonomous driving, so those two are the use cases which I will discuss in the later slides. In the case of the autonomous driving, we want to understand what is the cause and effect of a collision. Which vehicle led to the collision? What was the effect of that? And whose fault was it? So these type of questions could be very interesting for insurance companies. That's what they specialize in. But the first step in doing all of these things is to learn causal relations in the domain and the data. We can do all of these great things, but the very first basic concept is how do we learn what are these relations in the data or in the world around us or in any domain that we want to deal with. So this is a quote which I really like by Gary Marcus, where he says AI needs fundamental representation of space, time, and causality. So to actually develop AGI, artificial general intelligence systems, we need these fundamental representations about learning about what is a space, how does things change by time, and the effect or these relations or the explanation of causality. Now coming to the root cause analysis problem in the smart manufacturing. So typically what happens if there's a downtime in any factory, that downtime can cost the industry or that company amount of it from 50,000 to it could be 500,000 per hour. That's a huge amount or a huge loss for the industry or the company in that case. So how can this causal neuro-symbolic AI techniques can help? We can do, as we said, root cause analysis to analyze the defects and anomaly where it happened. We can use symbolic AI to incorporate safety critical protocols. We can use causal models to analyze the potential causes of a safety violation. We can reduce the downtime by quickly understanding the failure modes, the causal relationship between the machine performance, and we can easily predict maintenance needs and minimize downtime beforehand. It can assist in efficient resource management. So the models can enable us optimization of resource allocation based on the demand, condition, and assembly processes. So we can be prepared earlier rather than when the problem arises. So for example, in the case of COVID, many of the industries or factories were not equipped well enough to get the huge amount demand, especially in the case of masks or the medical equipments were there. But what if they could have a more causal model which could analyze the relationship between different variables, and they can easily scale when such a need arises rather than deciding it at the time of the need. So what are the challenges that we have here? Identifying the root cause of an anomaly in a complex system where there are multiple independent components, which makes it extremely difficult for analyzing it and obviously for preventing future use cases. What could be the solution? For this case, we could do causal reasoning. It can help us trace back where did the fault occurred, why did it occur, and how can we try to mitigate it. And what could be the impact of this? That it could reduce the reoccurrence of faults, lower the risk of cascading failures, and improvements in component reliability. So we have the setup is from our university. So this lab is in McNair Center, and this is known as, the lab is called a Next Smart Manufacturing. So what this lab is doing, they're assembling a toy rocket. That's the green rocket that you see here. There are 4 parts of this rocket. There's a base, there are 2 body parts, and the nose. And they have this entire system there, which is in the middle and the rightmost image there. They have 4 robots which are assisting in assembling it, and then deconstructing it, and then putting it on the assembly cycle again, just to learn how to assemble a toy rocket. And what happens sometimes is there might be an anomaly there. So the way we define anomaly is there might be a rocket part missing. So there might be a nose missing, which is the topmost part. There might be one of the body parts missing, which is these 2 cylinders that you see here. There might be the base missing. So these are the anomaly. And we want to see why did that anomaly happen and how can we mitigate that, or which rocket caused that anomaly, or which robot caused that anomaly. What was the sensor value that was associated with those? So here's the data that we have. So we have a couple of rows in the sensor values here. It's a CSV file where you have the values for load gripper, potentiometer sensor for each rocket. We have the information about the angle of the robot, We have the information about what was the temperature of the conveyor belt, where was the rocket at the time. So we incorporate these sensor values. We developed an ontology. I'm not sure if people are aware of an ontology. So ontology is a taxonomy. You can think about it. And so we developed an ontology for the system. We used the sensor values that they have, and we created a knowledge graph out of this. And now we can use this knowledge graph to query and ask, given a no nose anomaly, so there was a nose missing, which frame, which is the data set that we have, which frame that is which time frame and the assembly cycle was it associated with it. And it can give you it saying that the cycle was the third cycle where it happened, and these are the UUIDs, which are machine readable for where which frame this anomaly was associated with it. So as you can see, there were 3 different frames where this anomaly had happened. And now we want to see, why did that anomaly happen? So why? We had to answer a question of causality or causal reasoning. What was the relationship between different variables in this data set? So typically, the way it is done, you're given the data set and you learn the causal Bayesian network. So if you remember, the Bayesian network was with this variable C, A, B, D. So you learn those networks, which tells you a structure that A causes B, B causes C. So which are the variables that might have caused? So just running the standard structure learning algorithms, this is the type of network that we got. So we got that there's a rocket tray, which is the MHS green rocket tray, where all the parts are there, and the rockets and the robots take those parts and try to assemble it. So that causes a cycle state. Then the cycle state, which could be cycle state number 1, 2, 3, then the cycle state is causing the change and the gripper potential of the robot one, I'm sorry. Then the robot one's gripper potential is causing the robot 3 gripper potential change, and so on. So if you just look at this network here, some of these nodes do not make sense, or some of these relations do not make sense. How can a cycle state, which is just a number, cause a change in the potentiometer? No, right? It should be the command that's given to the robot, which should change the potentiometer reading. Similarly, it says that the cycle state is causing the anomaly. How can a cycle state cause an anomaly? It would not. So basically what it means, every time the cycle state is 10, it would cause an anomaly. That's how causality works. Otherwise, this could be a spurious correlation. But that's not happening. So the argument here is, if you just take the structural learning algorithm or purely data-driven applications or approaches, you might end up with something like this, which might not make sense. So to avoid that, what we do is, we take this data or this network partially, not completely. I have a domain expert in the loop, or the human in the loop, who tells us which nodes, which edges make sense, which edges do not make sense. And we incorporate this relation into a knowledge graph and then use the neuro-symbolic AI techniques to do the causal task of root cause analysis. So why did we not use this network? The first is, some of these things don't make sense. Second question that you might ask is, why did we not involve human in the loop in the first place? They are extremely busy. So if this was a healthcare domain, it is extremely difficult to get the time of a clinician and ask them, hey, there's this 27 or could be 1,000 column Excel sheet, and can you please help me analyze which column is affecting what? They cannot do it. They don't have the time to do it. So we can start with this, give them something, and ask them, hey, which are the ones which make sense? And we can do the rest from there. But to do so, we obviously need a complete causal model, or a model which is good enough, not the one which gives you some spurious relations. So to do so, we combine, as we said, we have a partial Bayesian network, we combine into a knowledge graph, and we call it a causal knowledge graph. So why do we do that? Why don't we just use the Bayesian network? As we've seen that earlier. So what are the pros of? Obviously, it does have some benefits. So the causal network models the causal relation between the corresponding nodes, but it can different experts can at times give you different causal models. So if I have a different understanding of the word, I might say, no, your coming late is not caused by maybe the traffic, it's something else. But somebody else might say, no, it's the traffic, it's not the other issue that you have. The knowledge graph, what are some of the pros is that it has extensive domain information in that. So you might not have to sit with the domain expert and say, tell me everything about your domain. No, you can get that information from the knowledge graph. Some of the things that it is lacking is a causal relation, which Bayesian network can help us. So combining those two gives us a causal knowledge graph, which is nothing but just a knowledge graph where you have causal relation between entities in the graph. So if you just use the observational data and the structural learning algorithm, we get incomplete network. We take the incomplete network, as we have seen in the smart manufacturing setup. We incorporate that into a causal knowledge graph, and then we use the knowledge graphening prediction techniques to complete the causal network. So what are some of the advantages of doing so? Causal AI by itself is user explainable. We saw it from the Bayesian network that we have seen in the previous slides, that C causes B, everybody understood it. A causes D, everybody understood it. Causal neuro-symbolic AI provides additional semantics. So there could be some additional properties of the node C. There could be some additional properties of node D, which can be incorporated from neuro-symbolic AI. Causal AI is scalable? No, not really. They can deal with less amount of data. So they can deal with 500 at max to max 1,000 variables at time. But if you have the neuro-symbolic AI techniques, they can easily scale. So in the neuro-symbolic techniques, we use neural networks, which are easily scalable. Causal AI takes the observational data. Neuro-symbolic AI can incorporate prior knowledge from the knowledge graph, and so on. So there's another example that I'm going to give you guys. So here's this video, which most of the time does not help. I can show you later. So basically, this is a video where multiple objects of different shapes, size, and materials are coming in the frame, colliding with each other. And they have these, in the data set, this is a benchmark data set of called Clever Humans, which has these events, and it's a description of the events in the data set. So some of the events in the video are the brown cube collides with the purple cylinder, the purple sphere slows down, and so on. And this is a type of a causal network. So this says E is causing A. So the purple ball bumps the brown cube, is causing the brown cube collides with the purple cylinder in the video. And the edge weights here are actually causal weights, which are annotated by humans. They tell you how much E is responsible for the event A. So higher the number, that means higher the responsibility of A. So the number 3 basically is it's moderately responsible. There might be some other events which might be causing this event A. The number of 5, which is extremely causal, says that yes, E is extremely responsible in causing the event C. So we've seen that from the Bayesian network that they contain information at the instance level. We call it in the knowledge graph or the semantic space. They do not have causal roles. So by causal roles, I mean the treatment, mediators, and the outcome roles that we talked about. They do not contain additional context and the domain knowledge. So what could be the additional knowledge that we would want to incorporate? Which video was this event associated with it? Which object was it in this video? What was the properties of the object? What is the event that it happened? So there are different types of events that are occurred in this video. There's a collide, there's a roll, there is a push. Some of them are a single object event. So slow down is a single object event. Binary object events are something is hitting. So 2 objects are coming and hitting each other, or colliding is a 2 object event, and so on. So we take all of that information that we have. We incorporate this Bayesian network that C event is causing A is causing B into a knowledge graph. So this is a snapshot of what a knowledge graph would look like. So it would have a causes relation between C to A to B. It would have other properties. So C is a type of a move event. A is a type of a collide event. B is a type of a roll event. And then you have additional property that there's if the object is the brown cube, it has a property of a cube. It has this color of brown. And the C event has participants, so it has a participant, the brown cube, and so on. And we used a couple of ontologies, which are also developed in some are developed at the AI Institute. So we have causal ontology developed in the AI Institute. we used scene ontology, which is also developed by one of my colleagues, to come up with this knowledge graph here. Just for the sake of time, I'm skipping the knowledge graphs, but you can always ask me a question by at the end of the talk. We also have these weights which are on these edges, but typically these weights are not on the edges in the causal Bayesian network. You need to estimate it. So we do want to represent it in the knowledge graph. So we can use the weighted knowledge graph link prediction techniques. So along with these causal relations, we also incorporate these weights, which are typically not generally there in the link prediction techniques, but we come up with these weighted or a literal based link prediction techniques. Then coming up with the mediators, if you have remembered that we have this chain reaction where C is causing A is causing B. So if we just want to represent this Bayesian network one-to-one into a knowledge graph, this is how it would look like. That this is C is causing this, all of this at the knowledge graph level, which are, so C is causing A is a triple, A is causing B is another triple. Then there'll be a third triple which says C is causing B. But there's no triple which is telling us that C is causing A is causing B. That information is lost somewhere in the knowledge graph. So to do so, we created a hyperrelational knowledge graph. So what is a hyperrelational knowledge graph? Basically, you can associate additional properties to a particular edge here, or this is called a relation here in the knowledge graph. So we can describe it. All of this information which you see on the top can easily be described with this type of a representation, where you have a node C is causing B. This is the treatment. This is the outcome. And then you have this mediator A, which says that this relation has a mediator, which is this A, and it also has those additional property that A is a type of a colloid, C is a type of a move, and B is a type of a roll event. So now we want to do link prediction. So tell me what causes B, or what is B caused by, and so on. So this is a simple causal triple. Cause event, which causing an effect event here. And then we don't want to do predictions at the level of an instance, because into a knowledge graph, there could be multiple instances of something. We want to say what was the type. So if it was a medical knowledge graph, we want to ask a question, what caused a headache? There could be different instances. So instance could be, I did not sleep well, I was stressed out, at times so and so. We don't want to predict that. We want just for the granularity, or not granularity, but for the explanation's sake, we want to predict there was lack of sleep or stressed, rather than when were we stressed, when did we not sleep well. So to fix that issue, we define these reified relation we call, where you explicitly define a relation between an instance, which are these dotted nodes, to the type, which is the class level information. So we want to say what did the cause event cost, or the type of the effect event that has been caused. So we have this relation causes type. Similarly, we want to explain what led to the effect event, where we have this relationship of caused by type. So we define these two queries that we can ask, or tasks that we can run, which is causal prediction and explanation. So you're predicting the effect type. So you are given a cause event. Now predict what is going to cause. What would be the next step? And then explanation is, given that you have an effect, that you have a headache, what led to that headache? That's the explanation that you will be solving. So we incorporated all of those relations into a knowledge graph here. So this is the overall architecture. And we're going to ask multiple link prediction techniques, queries here. And we basically saw that the weighted link prediction, where you involve the relation or the weights of 3, 5, 4, and 2, 1, that performed better than the baseline link prediction techniques. And yeah, and incorporating the knowledge, which is the knowledge about what was the type of the event, what was the object participant in that event, that led to 31% improvement in the performance. So another use case I'll quickly cover in the next 5 minutes is the scene understanding in the autonomous driving domain. So just gonna ask you a quick question. Do you think there is a causal relation in the driving scenario? So when you're driving out in the world, is there do you have causal reasoning or a causal thinking of what's going on? I'll give you an example. The fact that I press the accelerator my car moves faster. So depending on how much I put the pressure, it causes the car to move faster. But what about other things in the driving scenario? So we got encounter pedestrian, there's a crosswalk, there's a stop line marking, sometimes there's a school bus, anything which causes us to do something with our car. Like what? We stop, right? If there's a stop line marking, we stop. If there's a pedestrian trying to cross, that causes us to stop the car. So these are all causal relations in the domain. So this is some of the causal relations we have. So you have a car here. So there's a stop line marking, which is causing the car to stop. There's a this stop line marking and the stop crosswalk here causes the pedestrian to walk. And the presence of both of these in the driving scene are causing the automobile or the car to stop. So we have this panda set data, which is another benchmark data set. We come up with this Bayesian network. This is on our own. And we,
so in this case, the scenario, I know it's a relationship, but irrespective of the star, the pedestrian there in the pedestrian crosswalk, the car has to stop.
Yes.
By seeing the stop sign. So how is it this is related to in terms of?
So this is the purple one, stop line marking is the treatment. The outcome is the car stopping. Right. So there's one relation. Okay. In the second relation, also the car will stop. The outcome will be stop when there's also a treatment and the mediator. So the pedestrian is a mediator here. So this is the Bayesian network in this case. So we have the data set, this Bayesian network, and we estimated something which is called as causal effects. So we have 3 different types of causal effects, which basically helps us answer those interventions and the counterfactual questions at the ladder of causation, the second and the third rung of ladder of causation. I'm not going to go into detail, but you can always ask, stop by and ask me at the end of the class, what are those causal effects and how do we estimate that? And we incorporated them into a knowledge graph, and some of the cool questions that we can ask using those effects is. So the total causal effect can help us answer what is the effect of a stop line marking on the motion of a vehicle. That is the interventional. What if there's a stop line marking versus there's no stop line marking? What would happen to the vehicle? There's a chance that 6.38% on the stop line marking has a positive total causal effect of 6.38% on the pedestrian walking as compared to the scene without the stop line marking in this scene. Then another question that we can answer is, what if there's a pedestrian, what if there's a jaywalking scenario, which typically happens time and again to us. So we can we can answer this question using the natural direct effect and querying the causal knowledge graph in this domain. So it basically tells us if there's an adult pedestrian with object, which could be a backpack or a stroller in a scene, assuming that there is no stop line marking, it would have a positive effect of 14.67% on the stopping of the vehicle in these scenarios. The other question that we can answer is, which is also practical, sometimes the stop signs or stop line markings are faded. So as humans, we can see there's a stop line marking, but it can happen that the autonomous driving vehicles can fail to detect those stop line marking. How would that affect the stopping of the vehicle? So basically, it would have a positive effect on the stopping of the vehicle because the vehicles would behave in accordance with the pedestrian trying to cross, not in accordance to the stop line the faded stop line marking which was there. So in conclusion, I think I'm on time. Combining causal AI and neuro-symbolic AI provides us some explainable results or explainable model. It makes the decision-making process more transparent. It provides understandable explanation for predictions made by neural network. They provide robustness and generalization. So even if you change certain parameters in the model, it would still give you the correct output. Using the causal models, they can improve the robustness to out-of-data distribution in the case of anomaly, for example. They can enhance generalization by incorporating domain knowledge. We can perform interventions, which we did. And using that, we can predict the impact of interventions and we can make informed decisions in those cases. And integrating causal reasoning can help us adapt to dynamic environments or new environments, for example. So, yep, thank you.
That's good, thank you. So guys, any question? Anybody has a question?
So one question on the, where it's a faded, crosswalk, right? But combining this neuro-symbolic approach, where if you know it's a faded, but there are rules written, like logic written, so the symbolic, let's say that the downtown or something like that, where the speed limit could be 35 or 45. Beyond 45, it could be a highway. But if within these limits, there could be a pedestrian coming in. So that can be a rule can be written where we combine both the causal as well as the neuro-symbolic approach, which can help us to, for the autonomous vehicle to act pretty quickly, right?
So that's what we tried to do in the Bayesian network that you saw. Both the stop line marking and this pedestrian is causing the.
No,
vehicles to stop.
that's a good scenario that stop line helps us to prevent the
Yes.
vehicle stopping it. There is the faded areas where that is the case right now. People are
Yes.
scared about autonomous vehicle these days, right? Because it's not all the road conditions are right, bumpy roads and a lot of other areas, but the combining both neuro-symbolic with the causal AI can say that, okay, this areas, there could be a speed limit of 35 or
Yeah.
40 where people might cross because that is people can walk in the road, right? So not applicable for highways.
That's right.
Also, one more thing to add to this, if you have looked into any of Tesla's code on GitHub, right? One of the things that they initially started off with, like the older versions of it, they used OpenStreetMap's embeddings. So OpenStreetMaps has this access where all the data that is with the city council is loaded into the maps. So even if you have no stop sign, like the paint is completely gone, there's a new road over there, they're still constructing it. The autonomous vehicle will still detect that there is a stop, there is supposed to be a stop sign and take that into consideration.
But if
There are very
the-
rare cases where, it is not updated in the system and there was a new stop sign that they are building right now, for which it won't. So which is why you're seeing like accident rates of Teslas are almost very low. And one or two of those things, they'll definitely try to highlight it out because, they want to, of course, they try to find flaws and need to be correct.
But it's a good example of car as an example for this one, but yeah.
Exactly.
Wonderful. So, yeah, we can start. So with regards to, well, this was the last class. I